Okay, this is the second part of a lecture on derivatives of exponential functions. We learned that y equals a to the exponent of x, the exponential function, where a, the base of the exponential function, is positive, but it cannot equal to 1. The derivative is a to the x times ln of a. We proved that. And we also said that if the base a happens to be the number e, then y equals e to the x has a derivative that is equal to itself. Now, combining these two formulas with chain rule, we can come up with two more formulas. So I can write here, instead of a to the x, I can write a to the exponent of u, and u is a function of x. So the derivative of a to the exponent of u would be, of course, a to the exponent of u times ln of a, of course, and then times u prime. That comes from the chain rule. Derivative of e to the u would be e to the exponent of u times u prime. Okay, so u prime times e to the power of u, in other words. So these are four formulas for the derivatives of exponential functions. Okay, whether they're in the book, they're not in the book, it's okay. We just learn them. All right. These are a whole bunch of examples that shows how we apply these four formulas. The first one is 2 to the exponent of a quadratic function. So it reminds me of a to the exponent of u. So the derivative would be u prime times a to the u times ln of a. So u prime is just 2x, and then times a to the u, which is 2 to the exponent of x squared minus 5, and then times ln of a. In this case, it will be ln of 2, and that's the final answer. Next one is e to the power of cube root of x. Okay. E to the exponent of cube root of x, which means that u, the function of x, is cube root of x. So following the formula, the answer is u prime times e to the u. So u prime is the derivative of cube root of x, which is 1 over 3 times cube root of x squared. That's the derivative of cube root of x. That's u prime term. And then times e to the u, which means times e to the exponent of cube root of x itself. So this is the final answer for that derivative. We used this shortcut formula, which combines exponential derivatives with chain rule. This next one is a product, x cubed times e to the x. That's a product. So it's going to be u prime v plus v prime u. We have to apply the product rule. So it's going to be 3x squared times e to the x plus the derivative of second times first would be e to the x times x cubed. Of course, you can factor common factors here. I would say x squared is common, e to the x is common. So if you factor out, you get 3 plus x simply. That's the simplified final answer. Next one is a quotient. So quotient of two exponential functions. Derivative of top would be negative 2e to the exponent of 2x. We are using this formula, e to the u times u prime. What plays the role of u is actually 2x. So u prime would be 2. I did write it. There was a negative sign in front, and derivative of 1 is 0. So negative 2 e to the x, that's the derivative of top, times the bottom. So this is derivative of top times bottom, u prime v. And then minus v prime u, derivative of bottom, which is 2 times e to the 2x times the numerator. And the whole thing, of course, divided by the denominator squared. So now, perhaps we can simplify this. Negative 2 e to the power of 2x. With this negative 2, if you add them up, it's going to be negative 4 times e to the 2x. And then when I multiply these two, I get positive 2 times e to the exponent of 4x. Here I get negative 2 times e to the exponent of 4x. Now, why do I add the exponents? Because in multiplication of powers with the same base of e, we just write one of the bases, simply add the exponents, and 2x plus 2x is 4x, obviously. And this one is the same thing, but it's plus, so I think they're going to cancel out each other. the denominator remains unchanged. So final answer, after I cancel out those two terms in the numerator, is going to be negative 4 e to the power of 2x divided by 1 plus e to the power of 2x all squared. So that's the final answer for this derivative. We have 10 to the exponent of square root of x in the next example. So that reminds me of a to the exponent of u, because the exponent is square root of function. It's a square root function. So that plays the role of u. I'm going to apply this formula. These formulas are becoming very, very handy. So a to the u is itself. So it's going to be 10 to the exponent of root x. U prime is the derivative of the square root, which is 1 over 2 times square root of x. Okay. And then we have ln of a. So in this case, it will be times ln of 10. Okay. Because the base, a, in this case, is 10. Plus, that's 9 to the exponent of pi x. So I'm going to apply the same formula again. The answer would be u prime, which is pi, because the exponent is pi x. The derivative of pi x is pi. So that's going to be pi. And then a, which is 9 to the exponent of pi x. And then finally times ln of 9. So ln of 9. That's the final answer for that question. So you see that all you have to do, learn these formulas very well and try to apply them. This one is cosine of the sum of two exponential functions. So cosine of u, the derivative was negative u prime sine of u. So negative u prime times sine of u. That's the formula we have learned in the past. We learned formulas for the derivatives of trigonometric functions. Now, what is the derivative of inside? What is here playing the role of u prime for me is the derivative of e to the x, which is itself, and derivative of e to the negative x is negative e to the negative x. So negative e to the power of negative x. You can multiply if you feel like it. You can say it's e to the negative x minus e to the power of positive x, multiplying negative 1 by every single term inside the brackets. And then we have the same thing, sine of e to the x plus e to the negative x. So again, final answer. This one is tangent of some function of x. That's tangent of an exponential function. So this is tangent of u basically. Now, derivative of tan of u is u prime secant squared of u. So derivative of inside times secant squared of 2 to the exponent of x. But u prime here, which is the derivative of 2 to the power of x, can be found by using this first formula here, because a is 2. So the answer is 2 to the x times ln of 2, and then times secant squared of 2 to the exponent of x. Next one is 2 raised to the exponent of tan of x. So what plays the role of u here is actually tangent of x. So I have to use this third formula. This reminds me of a base of a, which we have before, raised to the exponent of u, which in this case is tangent of x. And the answer is right there. So it's going to be 2 to the exponent of tan of x. I'm going to rewrite it. And then times u prime, which is the derivative of tangent of x, which is secant squared of x. So that's u prime. And then times ln of a, in this case, times ln of 2. And that's the final answer. You see how we are applying these important shortcut formulas. The last one is a product again, e to the x times ln of x. Derivative of first is itself times the second plus derivative of the second, which is 1 over x, times the first. You can always factor out the common factor of e to the x. So you end up with 1 over x plus ln of x inside the brackets, and you factor e to the x outside, just like that. So I gave you 1, 2, 3, 4, 5, 6, 7, 8, 9 examples of different functions. I try to combine trigonometric functions, logarithmic functions, exponential functions. I try to combine product rule, chain rule, quotient rule, and I give you these examples. They may seem crazy a little bit. You will probably not find these kind of exercises in the textbook, but it doesn't matter. We are just learning, okay? The most important thing you have to know are these 4 formulas. Just learn them very well and learn how to apply them, and keep practicing and keep practicing, okay? Thank you very much, and we're going to continue with the next lecture. Bye-bye.